have a resource which can do a heat transfer or a work transfer. I'm interested in some work transfer. Suppose let us say there is a wind flow or a water flow or a solar energy, anything. I'm interested in getting some amount of heat transfer or work transfer. I may be interested in air conditioning. I may be interested in electricity. But it looks like, according to the first law, in between the resource and the demand, whatever I require, the system will change its energy. So the energy of a system coming in between your ambitions and your resources. If you don't know how to manage, maybe all the resource may be taken by the system in the form of energy, you are left with nothing. So that's a very interesting way to understand what to do. Okay, the create resource of parallel to nature is the goal of this energy. Uh, there is nature and create a resource from the nature and then try to use everything. So coming back to this particular point which I was discussing in the last class, that's the reason you should understand the fact that energy comes in between your ambitions and your resources. If you don't understand this one very clearly, you may end up consuming all the resource to increase the energy of the system, but you get nothing. So that is not the ambition, that is not the engineering. All forms of energy which will change because of the heat and work transfers, obviously, will have a two categories, as I said. Some are macroscopic, clearly visible to us. Some are microscopic and very latent. Unless you are very careful, you will do lot many engineering mistakes, if not scientific. Okay. And within the microscopic or a macroscopic, you will need to understand that a microscopic energy could be a potential or a kinetic. Similarly, macroscopic energy also could be potential or a kinetic. Again, there is a problem. If the most of the energy is in the kinetic, easy to sense. If the most of the energy is in a potential, sometimes very tough to understand. I'll give you examples. This particular four-way energy is very essential. What is microscopic, kinetic and potential? What is the macroscopic potential and kinetic, which you know very well. I don't have to tell what is the potential energy macroscopically or kinetic energy macroscopically. So as I was saying, the energy by the virtue of position and state, this has a strong bearing. Suppose if I have a H2O in the form of a water, if I want to increase 1 degree Celsius, I have to give more. Somehow this water becomes a steam. To increase 1 degree Celsius, I can give less energy. What is this one? What is the difference? 1 degree Celsius increase of a liquid water, 1 degree Celsius increase of vapor water. Why they behave differently? Means there is something which is referring to a potential. Okay, whereas kinetic is easy to, higher the temperature means more kinetic energy, easy to feel. So this is where the people wanted to, similarly the macro potential energy, which you know very well, gravitational strain energy. The micro potential energy is the one, a chemical bond, state, nuclear energy is one of the most powerful form of micro potential. And the kinetic energy, I'm opening. Kinetic energy is, even if it is a microkinetic, no, you have a sense. The temperature we can sense easily. So by the virtue of temperature, now what we are sensing is mostly kinetic part, but the latent potential part, no, sometimes difficult to understand. That's what I want to resolve as a newness or a novelty of understanding this particular one. Coming back to that first law outcome, the change in energy during the process. Del Q minus del W depends only on the initial and final states. It is independent of the path. That is what we have proven yesterday. So it is a differential of a property. The difference between delta Q and delta W is a differential of an unknown property, but we know this property much before knowing the theoretical scientific way called energy. So this property is energy of the mass and is given as a symbol E. Whatever mass of system is energy. Why I am using a mass is it is a extensive property. So that's how now the energy can be done for a small, infinitesimally small change. This is the one. If it is a finite change, you can have this one. Whether it is an infinitesimal or a finite change, the change in energy is independent of the path. Only endpoints will decide how much energy it is doing. This is another caution. And what I want to say here while taking the entire thing is, okay, you see this particular one. Suppose if the heat transfer is a resource, I'm interested in work transfer in between energy of a system coming in the way. If all the heat which I supply is consumed by the system to change energy and it gives nothing, then I am getting cheated. So I need to understand energy comes in the way between my ambitions and resources. That's why I want you to feel this particular kind of thing. So a general energy, generally felt, I am giving a general impression. There is a subtle thing which is ignored, which in a thermodynamics perspective. Basic science and physics people do appreciate this one. The microkinetic energy, well felt. I said it no. Our senses will change, sense the temperature. Why? Because the temperature makes us to feel the microscopic amplitude of vibration. I told you what is temperature. But there is a micro potential energy, but we can't feel. That's why we need to understand that very carefully. The next is the macro kinetic energy. Everybody feels the macro potential energy. We will discuss about these combinations plus one subtle micro potential energy. I am giving this expression the way people generally accept. But strictly speaking, I would have added micro potential energy, one of the most important which plays a role in engineering decision making or consumption of your resource and getting the entire thing. And what is the interesting thing is, though I am talking about the microscopic energy, the level of or the value of this microscopic energy depends upon what kind of system you have. Very interesting, no? It is a microscopic energy, molecular level of energy, and which is very essential to understand because most of your resource may be consumed in increasing the micro energy and you don't get back. All of us know. Everybody burn a coal and use some part, hot exhaust gases are going out. Whenever you run a car, your exhaust leaves with 450 Celsius, you don't know how to use it because that fellow has kept with it, I'm not able to retrieve. So that's how very important. The degree of microscopic energy depends upon macro shape of the system or the type of the system. For quite a long time people did not appreciate. That's why the conventional thermodynamics teach it in a indirect way, if not wrong. The first we need to say that suppose if it is an isolated system, I said it, no, grenades, etc. If there are internal energy changes, what is happening? How the internal energy changes when there is an isolated system. I am not giving anything at all. Even then, there can be any energy manipulations possible. The total energy is same, but one form of energy can become another form and create a danger. The next important thing is the control mass, and energy will change because there is a heat transfer or there could be work transfer or both. And during this time, if I give a finite amount of heat transfer, finite amount of work transfer, what is the change in energy? And how do I see that change in energy? How do I measure that change in energy, estimate that change in energy is very interesting. And similarly, suppose if I have a control volume, the moment there is a control volume, now you see this one, energy can change because of heat transfer, energy can change because of the work transfer, but there is an inflow, there is an outflow. Now because of which what will happen, incoming fluid can bring some energy, outgoing fluid will take some energy, and also there are two kinds of independent field for a micro. See, there is a container at the center, there is something flowing in, something is flowing out. The microscopic energy depends upon whether the given system and the fluid is it stationary or if it is moving. So that changes the entire degree of energy. That's why one has to be careful. Just to solve this problem, I am taking two distinct clear examples. Let us say I am producing steam. To produce the steam, I am burning some amount of coal or so. I have two options. One option is you have a big tank and can't you give a bullet here? Red bullet, not possible? Oh, so now you can see this particular one. You can fill with the good amount of water in a container and go on heating. Give a space, there is a steam, and whenever you want, you use the steam. So at the end of the day, I am producing a steam. This is one strategy. Now the next one is, no, I don't want to have any drum and storage, nothing doing. The water continuously enters and goes through the tubes, continuous tubes. And in between I am burning the coal and making all the heat to be transferred to this. Now in this case, continuously the fluid is moving. So you see this one, both are control volumes because something can leave or something can enter. And in the first case, there is a big tank which is having the entire thing. The second case, there is no tank, no container, the fluid is continuously moving. In these two cases, if I add a heat, how the energy is stored, how the given heat transfer is internally adjusted is a very interesting factor. First, let me talk about a container containing a fluid, and the fluid is not having an explicit motion at all. How the energy is stored physically, internally, that is the first one. Afterwards, I'll go to the same fluid, if it is continuously moving, will it be same or different? Very interesting. So because of this reason, people give a very pseudo models to explain this particular one, which I don't like. So first let me talk about microscopic kinetic energy. Again I am saying that why I am not taking the microscopic potential energy, because most of the time this microscopic potential energy is not explicitly felt, not even consciously noted. That is the biggest thing. That's why I am starting with this one. The energy is defined as an energy associated with the random disordered motion of molecules. The microscopic kinetic energy, higher the microscopic kinetic energy, more random, more disordered motion will occur. Oscillations or a random motion, Brownian motion, whatever this is, intermolecular forces. It is separated in a scale from the macroscopic order. This is not the macroscopic motion which we see. I showed you the example. In both the cases, there is a microscopic kinetic energy. But in one case, there is a clear-cut macroscopic flow also. By the virtue of velocity, there will be macroscopic kinetic energy. In the first case, it is a container. The container doesn't have any velocity at all. Even then, there is a microscopic kinetic energy. Very difficult to imagine. Very important to imagine rather. Again, it refers to invisible microscopic energy at the atom and molecular level. Very important. Unless you have a very thorough interest and focus, you cannot understand this kind of energy. The great people try to understand a type like a Boltzmann was one of the powerful who tried to understand a part of it, and he tried to understand only that one which is due to the random motion and kinetic, but he was not complete. Let us understand the Boltzmann, what Boltzmann could sense, what is not sensed, but still you are paying for it. Okay, very important. So the first level of energy, this is called internal energy, because the fluid is contained in a tank. There is no macro velocity, macro motion at all, and whatever energy which is contained at this point of time is internal energy, but whatever you can feel is only that part which is produced by the random motion. And that's how there is a kind of a confusion which occurs. Now I am going attractive repulsive forces at all, means no force by the virtue of the state. If at all there is some energy only because of the random motion. The people got confused that microscopic energy is only kinetic. But within a small time we could understand because of many engineering devices, many engineering processes. Please understand me, I am starting with the internal energy as a kinetic because that is more relatively sensible for a hand by the virtue of the temperature, but the same at a microscopic level, there are many forms of substances which not only have a kinetic energy, huge amount potential energy. If you don't understand that one, no, what will happen? You will use a resource, but all the resource cannot be converted into work, or a very little will be converted into work because you use wrong fluid which is not giving us at all. So very interesting and important. The more industrial research we do, and we see that we need to do more and more. The internal energy involves the energy on the microscopic scale. So very difficult to explicitly state it. And because the people started understanding with the ideal gas, and that too, if I take a mono, I can have energy very little. So because of which, no, it, even if I give a small amount of heat, it will change its temperature tremendously. You see the connectivity between this one. Simple people will be always open. Complex people, no, in spite of having a lot of money, they'll show up, okay, I don't have. This shows the openness of a substance. Like you see this one. If I have a system with the same temperature, if it is an ideal gas, that too monatomic like inert gas, only one way the system can absorb energy is by kinetic motion, the random motion of the molecules. In XYZ direction, it can have a linear movement. Suppose if I have polyatomic gases, they are ideal gases but polyatomic, like two atoms together, three atoms together. Now you imagine, instead of one atom, if the system has a 3 or a 2, now what will happen? They can rotate about axis, they can vibrate about a mean position. So because of which, now they have a more energy, they get a more capability to possess energy. Now what is the engineering consequence of this one? If the system is simple inert, I can give a less heat and increase the temperature a lot. But the moment the motion is complex, no, I have to give more heat to increase the temperature by 1. Now what is the meaning of this one? This fellow is not showing me the temperature at all. It is taking, but not showing the symptom. I think that I haven't given enough. That's how all my resource is consumed for doing something which is not useful to me. Now you can see this particular one. So if I take monoatomic gas and polyatomic gas at the same temperature, a polyatomic gas at the same temperature will have a more number of random motions, means more degrees of freedom, XYZ, and rotating about x-axis, rotating about y-axis. For each motion demands some energy. So whenever the number of motions possible, degrees of freedom possible is high, I have to feed each degree of freedom some energy to get a temperature change. Means explicitly I am wasting my resource on this fellow to give a unnecessary motions. This is the microscopic kinetic energy part. But if you go into the deal with, suppose if you take the liquids, these liquids are much more lavish. The solids are much more lavish. What is the difference between the ideal gases, liquids, or in between the real gases? The moment it is a liquid, not only random motion, they have a energy by the virtue of position. There are intermolecular attractive forces, intermolecular repulsive forces. Now these fellows, what do? You see this particular one, the microscopic energy. Suppose if I take an inert gas at some temperature, a polyatomic gas at the same temperature, and a liquid at the same temperature. Now this particular liquid will have huge energy microscopically than the molecular polyatomic gas. This polyatomic gas will have the same. Now, I am not concerned about this one, what it has, etc. But my problem is, if I want to increase the temperature of this one, the monoatomic will demand a least resource, but it will show increase in temperature. The polyatomic demands more energy or a more heat transfer to increase the same temperature, and this fellow will take lot. You imagine, if I have a 1 kg of water, if I want to increase the temperature, I have to give 4200 kilojoules of energy. Suppose if the same thing is a steam, okay, same temperature, water and steam, how? Forget about that, what is the pressure, etc. is a different deal. Suppose if I have the same thing at the steam, and if I want to increase the temperature by 1 degree, I need only 1900 kilojoules per kg. You see the big change. In one case, 4200 joules per kg. Why? Because as a liquid, it has a potential energy. Whatever heat I give now, it will store some as a potential energy, some as the kinetic energy. Unless I satisfy both the forms, I cannot increase the temperature. So it looks like one has to be very careful. If you are interested in creating a temperature, you need to understand whom should I pay my energy. Otherwise, somebody will take all the energy, it doesn't show up. Then I am getting cheated, because somehow I need to know what is happening to my energy. This is where the more and more. You imagine I am giving a good picture of being solid also. If I take a 1 gram of water at 0 degree and 1 gram of copper at 0 degree Celsius, both are at 0 degree, both are 1 gram. But if I want to increase the temperature by 1 degree, the amount of heat required or a work required, whatever we do, you can increase the temperature by heat transfer or work transfer. That is immaterial for me how you are doing, because I am talking about energy. How do you reach a state doesn't matter at all. Now you see the diagrammatic. This is the difference. The water contains a huge amount of potential energy, but kinetic energy part in the case is the same. So this is what is the Brownian sensate. The Boltzmann thought that all the energy which is possessed at a micro level is only because of the temperature and the random motion. He tried to give a formula based on the kinetic energy. But there are some people who are not as good as ideal as a gas. They are very non-ideal. They are very selfish. They have a lot of the things which are unknown. So that's how one need to be very, very careful. The same temperature implies that average molecular kinetic energy is same. However, one will take a lot of energy as a potential, the other will be almost negligible. So that's how the people got confused. I'm not able to define this one. That's why what I did finally what I did, for every substance, I created what is called a new property-like definition, which is highly deceptive, strictly speaking. I don't like the concept of specific heat at all. It is very convenient for engineering, but it spoils your creative thinking and utilization. So that's how we created a concept called a specific heat. And every substance, the specific heat is different. That's why to increase 1 degree Celsius, somebody requires more, somebody requires it. It is satisfying yourself. But I need to understand why this fellow has a more potential energy. Is it right to use this one whenever I want a temperature symptom? Or when should I use high potential energy substance? When should I use a low potential energy substance? After all, I am consuming my resource, maybe burning a fuel, maybe solar thermal, maybe geothermal, all is used. In between there is a system which is playing a role. Why should I unnecessarily waste my resource just by increasing the energy of some substance wrongly selected? Very important to appreciate. The specific heats are not the same is just satisfying your requirement. But that is not the reality of innovation. In an innovation, no, I need to know, because this fellow has a more potential energy, it demands more resource, it consumes more resource to increase the temperature by 1 degree. Why should I use him? If I, instead of the water, ice, if I use a copper, perhaps it is easy. Okay. So these are the ones which are to be understood very, very carefully. And the entire thermodynamics knowledge becomes engineering thermodynamics if and only if you give an engineering judgment based on this particular thing. CP of this is high, CP of this is low, specific heat of that is good, that is bad. That is not engineering. That is only science. if you are not able to take a decision to reject something, to select something, to prefer something, then there is no engineering in thermodynamics at all. That is the reason why I am trying to consolidate. Now you see this one. I am talking about the internal energy. When the internal energy is important and when the entire fluid is contained in a vessel and it doesn't have the explicit velocity at all. So though the reality is this, but whatever may be the substance, but the kinetic energy part is always same. Because Boltzmann mostly studied the ideal gases, he thought that the temperature can be easily calculated. Why temperature, increasing temperature requires more energy, and he tried to develop a formula only for the kinetic energy part. But the potential energy part is a suspense. Suppose if I want to take the potential energy part, people have to depend upon a specific heat. So now you imagine, suppose if I take a ice, till some temperature, by adding the heat, I can only increase the kinetic energy. Kinetic energy part will be slowly changing. Suddenly, when it reaches a saturation temperature, all the potential energy is supplied. That's why no, there is an enthalpy of or a heat of melting. Means unless I feed this potential energy, this will not change. The moment I feed the potential energy part, then water becomes very easy to be heated. Similarly, when I go on adding the heat to the water, it will reach a saturation temperature, which I was telling. The moment I reach a saturation temperature, it will demand a lot of potential energy. After that, no more potential energy. Potential energy is bare minimal. Why? The vapors are the one which has the least potential energy. If the vapor behaves like an ideal gas, almost zero potential energy. Only the thing, if it's a polyatomic, more degrees of freedom, more energy per degree Celsius. Okay, this is the theory. So this helps a lot in selecting a substance. Whenever you are doing an engineering, your objective of your engineering decision making is only to create highest possible temperature. It depends upon what is the working fluid, what is the substance you are selecting. If you select a wrong substance, you burn lot of coal, but temperature will be low. Then what will happen? Because temperature is low, you will get a less amount of work because you don't know that there is an energy. The temperature is one which shows the capability. Entire thermodynamics was developed because of one particular query by young boy called a Carnot. Suppose if I see the ideal gas. Now what is the beauty of the ideal gas? No potential energy. And all energy, microscopic energy is only kinetic energy. Now if I give a more heat and more random motion, because of the more random motion and the way Boltzmann said, more temperature. So if I use an ideal gas with a less resource consumption, I can increase the temperature. The economic way of increasing. In fact, no, using an ideal gas means the best engineering way of producing a temperature. That too, if the ideal gas is an inert gas, the minimum cost, and you will get the same temperature. Wonderful way of creating a temperature. But the potential energy is associated with the intermolecular forces which are present to be zero when it is an ideal gas. If it is a real gas, a mild amount of attractive forces. If the same real gas started condensing and becoming a liquid, huge amount of potential energy. Same liquid, if it is frozen to a solid, huge amount of much more. Why? This particular potential energy is the one which it doesn't show up. Okay, and you are wasting your energy. That way, heating a liquid was heating a vapor. There is economy of engineering. Only one way microscopic energy could be sure, only due to the random motion, that is only kinetic energy. If that is so, why it is different between the liquid, vapor, ideal gas? All are at the same temperature, but each one has a different energy. Then they try to explore and got the, this helps us selecting a working fluid from the nature. Sometimes all the natural substances are not useful, have to invent a new working fluid, that is called a synthesis of a new substance as per the thermodynamic requirement. For a monatomic ideal gas, the change in internal energy is very easy, all of you know very well. You see this one? If I have a monoatomic and the amount of energy required is 3 by 2 into RT. Why 3? There are 3 degrees of freedom. If I take a monatomic solid sphere, it can move in X direction, it can move in Z direction, can move in Y direction. For each direction, whenever I want to increase the temperature, no, there is a more amplitude in the X, more amplitude in the Y, more amplitude in the Z. They behave very democratically. So because of which, no, unless I feed all the 3 directions, temperature will not increase by 1 degree. Suppose if I have a polyatomic, along with the translation, they rotate. Then what will happen? I have to give more energy to increase 1 degree Celsius. Very nice way. And assuming there is no potential energy. If the rotational and vibrational energies are involved, a polyatomic, then it is more. So you need to know F. What is the F? How many degrees of freedom a molecule can have? If I have a diatomic, how many degrees of freedom? If I have a triatomic, how many degrees of freedom? And if I have a very long chain, how many degrees of freedom? What kind of wrinkles, etc. So you need to know degrees of freedom. How many motion? Why? Each degree of freedom requires some energy, because whenever add the energy, amplitude of all possible motions will increase. Then only 1 degree Celsius. This is what is called in physics equipartition of energy. Whatever energy or whatever heat or a work you do on a system, that particular heat or a work is used by the system to increase the energy, but that energy increase is done in such a way that in every direction equally distributed. This is called law of equipartition. Suppose if I have a substance, unnecessarily more degrees of freedom, I have to pay more. And over and above, not only kinetic energy, it has a potential energy to feed, then you will have a more and more. That cannot be calculated by this formula. For liquids, you cannot use this formula. For ideal gases, it is easy to use. And knowing the number of degrees of freedom also easy. How many number of amplitudes it can have, X, Y, Z, rotating around X, rotating around a Y. If I have a diatomic, it will have a XYZ motion and it can rotate about one axis. Okay, it can rotate about another axis, and triatomic more and more. So the degrees of freedom is the 1. So that's how whenever I have a control mass and whenever I do the heat interaction or a work interaction, and the energy of the system also changes. Now as I said it now, I am interested in working continuously. When I am working continuously, I want to know instantaneous. That's how. Let me consolidate everything together into one piece. So because it's a control mass, I don't have to care about how mass is changing. Mass will never change because it's a control mass. Nothing enters, nothing leaves. So automatically the mass should conserve. The conservation of momentum, all of you know, depending on how the momentum changes with the time. In a control mass, unless momentum changes with the time, there can't be a force. There is no other way of creating a force. There has to be temporal variation of velocity because mass is constant. So that's what the Newton law talks about. Newton's laws of motion talk about. The next thing is conservation of energy. What is that one? Yeah, first law of thermodynamics. So in order to change the system temperature, system energy, okay, so heat transfer can change, work transfer can change both. Now you can see this one. If you are very smart, you can do the entire process in such a way that the rate of change of energy of the control mass is 0. All the heat transfer can become work transfer. All the work transfer can become heat transfer. This is a process. I am not talking about anything else. It looks like. So the people wanted to do how to use my resource most effectively. What is the best process which will utilize my source completely? All of you think here. Suppose if I have an ideal gas, the ideal gas absorbs energy only because of the kinetic. So how do the kinetic thing, the change in temperature? Suppose if I add the heat in such a way that the temperature of the system doesn't change, then what will happen? All the heat may be converted into work during the isothermal. So that's how no, the great visionary, the Carnot, thought that best way of adding the heat is at a constant temperature. If I add the heat at a constant temperature, all the heat can be converted into work, but the temperature should remain constant, and it is a process. Now, how to take the temperature to be very high level? How to bring back the temperature to low level? That is the one which is the next step. Very interesting way of using a resource. But the next thing is the control volume. As I said, no, most of our real equipments are control volume. Some mass can enter, some mass can leave. Then what to do? You need to account for the mass. Okay, can I get the whiteboard? Okay, suppose if I have a control volume and where something can enter, something can leave. Okay, so there is something which is entering, something is leaving. Now this is the, if I draw a boundary, this is my control volume. Okay, this will contain whatever comes will stay there for some time, and something can leave also. So I can say there is something entering m dot in, something is leaving m dot out, because the moment it is a flow, you have to give a flow rate only. And now this is the mass of the control volume. Now the moment it is a control volume, the mass of control volume can increase or decrease by satisfying the conservation of mass also. Unlike a control mass, where, because what is the meaning of control mass? Mass cannot enter and leave. Then conservation of mass is mass of a control mass cannot change. Suppose if it is a control volume, mass can enter and leave. So whatever mass entering can get accumulated. Maybe the amount of mass entering may be much less than the mass leaving, or amount of mass entering will be much higher than the mass leaving. Then what will happen? Automatically mass of a control volume will change. So by satisfying the conservation of mass, if it is a control volume, the mass of a control volume can increase or decrease depending on the situation. So that's how I need to be very careful. Now similarly, you see the beauty of this one. Suppose if the mass is entering, now this will enter with some velocity, some pressure, some temperature. Sorry. So the moment the mass is entering, the mass will have some velocity of in, some pressure, some temperature, and the mass which is leaving will also have some pressure at the outlet, some temperature at the outlet, some velocity at the outlet. This is the velocity, capital V I am using. Now the moment there is a mass flowing in, along with the mass of the flow, there can be some momentum entering, because mass flow rate into velocity is a rate of momentum. Because of the continuous entering of this particular mass flow rate, there is a momentum added to the system. And similarly, continuous leaving of this one, there is a momentum leaving the system. And because there is a pressure and temperature and velocity, some energy may be added, some energy may be taken out. So that's how whenever it is a control volume, one has to be careful about auditing and balancing. If it is a control mass, very easy, because no mass entering, no mass leaving. If at all energy changing means there should be either work transfer or a heat transfer or both. Without that, perhaps energy of the system cannot change. One form of energy can become another form, but the total energy of the control mass should remain constant. So these kind of things will make it more go to the desktop. Okay. Now you can see this particular one. If I go to this, go to the slide more. Now you see, for a control volume, one has to be careful. The conservation of mass should be applied along with all. The rate of change of mass of a control volume depends upon how much is leaving instantaneously, how much is entering instantaneously. If the more enters and more leaves, automatically there will be a difference. Similarly, the conservation of momentum. Every entering fluid will bring on some momentum. Every outgoing fluid will take some momentum. So you see the beauty of this particular one. And wonderful way of creating a force using a control volume. In the case of a control mass, these two will not be there. These two will not be there at all. Now if at all I want to generate a force, mass cannot change. The a control mass should accelerate or decelerate to produce a force with time. Now see the beauty of this one. In a control volume, I can create a force without changing anything with the time. When will that possible? If the rate of momentum leaving is more than the rate of momentum entering, even if nothing changes with the time, there can be force created. That's how whenever the aircraft is moving, the entire aircraft is moving with the constant velocity. Air entered with the low velocity and hot exhaust gases will leave with a high velocity. Now you will get a thrust. The entire aircraft moves forward and there is nothing changes with the time. That is the greatness of a control volume. Means these kind of control volumes. Now the bigger question is conservation of energy. Now when it is a control volume, it is not just work transfer and heat transfer which can change the energy. There is a lot of fluid coming in, lot of fluid is going out. This coming and going in will have their own way. And how did they possess the microscopic energy? Even that is also very different from a container. So I am giving you the expression, and this expression is the rate change of energy dECV by dt of a control volume changes because there is some energy flowing out and there is some energy flowing in. And how do you estimate that one? And what are the parameters which will affect this volume? And of course, in any case, energy can change because of heat transfer or a work transfer. Now, whenever I have a control volume, no, changing energy of a control volume has a many ways. I can have a q dot 0, w dot 0, q dot in 0, this theta dot in 0, only leaving, automatically energy of the control volume decreases. Or no theta dot out, no heat transfer, no work transfer, lot of fluid is coming in. All of you imagine when you go to the bathroom and you have a cold water and pour a very hot water. Slowly the bucket water becomes warm and nothing going out. And you are not doing a heat transfer, work transfer explicitly. Only because the hottest water is entering into your bucket, your water becomes warmer. So you can manage everything. Changing the energy of the control volume has many ways. Now what is the idea is, this flowing fluid, how its microscopic energy will be different. The people did an explicit experiments and a lot of discussions led to a very beautiful understanding. Give me the whiteboard. Now let us take a control volume, okay, and it is connected with a inlet, okay. So now there is a fluid continuously flowing through and all will get accumulated in the container, okay. So now the thing, the microscopic energy in this one, the microscopic energy in this one should they be same? Suppose let us say all the properties are same, like the incoming flow pressure, temperature, specific volume, and the container fluid pressure, temperature, specific volume, all are same. And should I say microscopic energy is same or not? For that one, again you need to look into this one. One need to understand if the fluid is flowing, all the molecules are freely moving or atoms are freely moving. Whereas in the kinetic energy, they are moving in some random direction. But here they can move in some other direction. And it took a lot of study. If I want to increase same fluid, same pressure, same temperature, everything. In one case it is flowing, in the other case it is contained in the container. Now the people know, if I want to increase 1 degree Celsius of this particular temperature and 1 degree Celsius of the one which is contained here, the amount of heat required was different. Our amount of work required was different. Then the people got surprised. So both are same substance, both are at the same pressure, same temperature, same volume. How can this fellow demands more resource than the other? Then the people understood very carefully, lot of work is done, and they have understood that suppose if it is a stationary fluid, I told you, no, the increasing internal energy is F by 2 RT. Forgetting about the potential energy part, because I don't know how to understand this one to start with. That's why I invented a specific heat, very convenient way. Okay, suppose if it is a flowing, this F by 2 will become F plus 2 by 2. Means you need to feed 2 degrees of freedom extra. And this particular one is explained in thermodynamics books in a different way. I request all the teacher to explain that one. A flowing fluid possesses more microscopic energy, and these microscopic energy in general found to be 2 degrees of freedom extra. So that's how I cannot call these two same. Both are at the same temperature, but the amount of microscopic energy is different. What should be the name given to? This is given a name called delta H. This is called an enthalpy. For an ideal gas or a vapors, it is easy to connect them and very different. That's how the people define the H is equal to U plus P into V. I'm not deriving this one because of our own, because I need to cover something which is very exclusive. Now you should see this one, very important. Whatever analysis written in thermodynamics book is only to justification the real, and you need to link them both. Suppose if I want to do work or do heat transfer on a continuously moving fluid, I need to pay more. Similarly, a continuously moving fluid will do more work, more heat, unlike a container. And this, because of this, people give a very different thing, but I am giving more fundamentally, and the explanation can be used locally as per the requirement. Okay, so the moment we come back to, and finally we'll come back to our overall objective of thermodynamics, developing cyclic devices. And a cyclic device is developed by connecting many control volumes or a control mass alone. Okay, so let me show you how this first law will help us in creating more and more products. I am giving one example, and you can take more and more in the classroom as a solution. Okay, go to. Okay, I am trying to consolidate in the engineering perspective. So thermodynamic nature of variables in a control volume. Generally, how the control volume behavior in the thing. The incoming and outcoming mass flow rates are steady. In thermodynamics, we always consider m dot in will not vary with the time. M dot out will not vary with the time. If they are varying with the time, you cannot solve using a thermodynamics. You need to know fluid mechanics, or a higher order fluid mechanics also required. But within the thermodynamics, whenever there is a control volume, whenever there is a moving fluid, we always solve assuming the mass flow rate of moving in or moving out doesn't vary with the time. Steady means not varying with the time, very important. And properties of incoming and outgoing fluids are always constant. They will not vary with the time or vary with the space. And if you want to take this into consideration, you need to go for a higher level of thermodynamics. Properties of CV, that control volume, the container. One is the incoming, outgoing. So whenever there is a control volume, within the control volume there are two distinct features of substance. One is a part which is flowing in or a flowing out, which will have a different behavior. The part which is in a container. Suppose if I have a control volume, no container at all. I have shown you an example. There is a control volume, only pipeline. Nowhere there is an accumulation. Everything is moving. Then it is a homogeneously behaving a single way. The moment I have a container in between, then the issues are different. Then there is a explicit control volume, a container, and which can have a variation of property throughout the system, or its properties can vary with the time also. Inhomogeneous means a property variation in the spatial direction, one point to another point. Variant means properties varying with the time. Okay. The following features of control volume are generally possible. You can have inhomogeneous variant, difficult to solve using thermodynamics. Okay, means some control volume, the properties are varying in the entire space, also with the time. For that one, no, we use a modern, very modern, many systems learn. You people may learn when you go to higher degrees. It is called a computational fluid dynamics. We will not solve using a thermodynamics. Computational fluid dynamics is nothing but very detailed thermodynamics. People will not just call it as a thermodynamics. And the next one is homogeneous but invariant, means all the system will have only one property, but at a given time the system will have only one property. As the time changes, property will change. These are called homogeneous but invariant. Sorry, homogeneous invariant, sorry. A trivial solution, nothing is happening to the system, no change at all, sorry. The next is inhomogeneous and invariant. Generally we call it as a steady state, not changing with the time, but inlet to exit. I gave you an example of a jet engine. I'll show you again. The next is the rate of work and heat interactions can vary with the time. The Q dot and W dot need not be constant with the time. Slowly they may increase, slowly may they decrease. You imagine you started the car from zero velocity, the slowly it will accelerate. So because of which the rate of heat transfer, work transfer will be different. Suppose if you are traveling on a highway at a constant speed, perhaps work transfer and heat transfer rates will be constant. Afterwards, you are about to reach the station, you will apply a brake. Now automatically heat transfer and work transfer will change with the time and suddenly come to the rest. Okay, so this is possible in a reality. The third one is homogeneous and variant, which is called a transient systems. Okay, and generally in engineering or in thermodynamics, we use these ones, steady state systems and transient systems. I'll try to give one example because this is the one which builds the entire globe. The modern engineering has a lot many steady state systems. That is the reason I'm using these particular thing. So I'm giving one application of this particular one, a means to estimate the size of engineering devices. Okay. Now let us say there is an aircraft and this aircraft took off and it reached the cruising altitude, generally 10 kilometer plus or so. After reaching 10 kilometers, almost all the aircrafts will travel with a constant speed. Nothing will change. Now all of you know, so there is engine, isn't it, which is attached to this particular wing. If you see closely what is happening to the engine, which is able to produce the entire force required to move and consuming lot of fuel, and if you look into carefully under a closer look, now you see this particular one, you see this particular engine, continuously air enters by the virtue of relative velocity, and this air is subjected to many thermodynamic operations because there are a series of control volumes inside, and finally what comes out is high velocity, high temperature jet. Now you see this one, the mass flow rate is almost the same perhaps, and it is entering with the less velocity. So rate of momentum at the inlet is less. Rate of momentum at the exit is high. Now the difference in the rate of momentum is the force. That is the action. That action is translated into reaction, and as a reaction entire aircraft moves forward. Okay, so this is the one you can have the first law for control volume, steady state, steady flow. There are many things. So this is the one. Suppose if it is a steady state, steady flow means nothing changes with the time. So most of the engineering systems, I'll give examples, they work like a steady state, steady flow. Or whenever I am designing a split, I assume them to be a steady state. Now you see, whatever comes in will go out. The mass of the control volume doesn't change. And no accumulation, no depletion of a mass. Next is the conservation of energy. The energy of the, because nothing changes with the time. What does it mean? Energy of the control volume should not change. Now, you see the beauty of this one. Some energy comes in, okay, some energy comes in, some energy will go out, and I may do some amount of heat transfer, I can get the work transfer. And the system need not change its energy at all. Very smart way, no? Because this particular system is coming in between the resource and my ambition. And unnecessarily system changes in energy, all the resources wasted in changing the energy of the system. Why should I waste my money? After all, why I am burning a coal? So that there will be a heat transfer and I'll get a work output. If the entire thing is used to heat the entire fluid, then nonsense. I'll be very happy. My car exhaust gases go at the lowest temperature possible. Then what will happen? I'll get the more work output. So one need to work for that one. And the goal of consuming a resource is not to increase the energy of the system, but energy of the system will play in between. That is the first law for a process. Whenever I develop equipment, I need to use a working fluid, and that is the working fluid which will help me converting heat transfer into work transfer or work transfer into heat transfer. A series of control volumes should be connected to operate a cyclic process forever, for a long duration. All these things are a requirement of this. So you see this particular one, very important. The most of the systems work steady state, steady flow, and these are very essential for developing. Okay, this is the one. By virtue of the moment you have a steady state, no, you imagine if it is a small aircraft, there is a small engine. Why it is a small? It is taking less flow. This engine may be self-similar to big engine. Suppose if I have a Boeing 747, I need a bigger engines. And maybe there are bigger engines which will have a 6 engines or a large engines also. Not only that. So whenever I am doing a research, while developing a research, I'll do a small engine only. Why? The cost of development should be minimum. Once I am happy with the entire thing, the same thing I'll make a bigger. So this is the beauty of steady state, steady flow. You can always develop a very small or a very large. They are self-similar. Only the thing which is varying is the mass flow rate. One takes larger mass flow of air, larger heat transfer, or work transfer. But they are self-similar per unit or for a in a way intensive. I am creating a kind of intensive. You see this one, the work transfer and heat transfer. The rate of work transfer and rate of heat transfer can be increased or decreased without changing anything. Pressure, temperature will remain same. But more mass, more work transfer. More mass, more heat transfer. So this is the beauty of steady state, steady flow systems. And most of the engineering cycles or systems are developed assuming them to be a steady state, steady flow. And tomorrow I'll close with the our main objective of developing a cycle and estimating the performance of that cycle. Thank you. Any questions? No. So this animation will be done in next class. Oh.